Welcome to my channel, and this is the #1 channel for structural insight and a place where you learn, build, and innovate. Today I want to tackle this question on the board, and this is the design of steel to BS 5950, and it is example number 4. The question reads: a 150mm thick reinforced concrete slab is simply supported on a universal beam of effective length 6 meters spaced at 3 meters centers. Select a suitable universal beam section in grade 43 steel S275 and check for shear, deflection, web buckling, and web bearing given the following information. So we have the QK, which is equal to 3.0 kilonewton per meter square. And as you know, the QK is the imposed load. So we have the finishes is equal to 0.8 kilonewton per meter square. And the length of stiff bearing is equal to 75 millimeter. And this is the plan. As you can see, these are the steel, 1, 2, 3, 4, and they are spaced at 3 meters center to center. And this steel is spanning at 6 meters effective length. So let us see how you can solve or handle such a question. So before I can begin solving this question, I want to capture the most important information on this column so that I can rub here and create more space for our calculation. So the length is equal to 6 meters, and the center to center distance is 3 meters. The grade is 43. So grade is equal to 43, and the strength of this steel is S275. So the QK is equal to 3.0 kilonewton per meter square, and the finishes is equal to 0.8 kilonewton per meter square. We have the length of the bearing is equal to 75 millimeter. Like that. So having done so, I can now rub here to create more space for our proceeding calculation, but I will preserve this drawing for our calculation. So solution. So the first thing to do is to calculate the loading applied on the universal beam. So loading. So under loading, we will calculate the dead load, which is GK. So GK is equal to self-weight of slab plus finishes. And then we'll come and calculate for the imposed load, which is QK. So let's now start with the GK, which is the self-weight of the slab. So I want to consider the middle beam on this slab. As you can see, you have this beam here. It is at the center. So this beam will support a half of this slab and also a half of this slab, like that. So we'll have this area being supported by this beam. So this is the area supported by this beam. So the distance of this area from here to here is 3 meters, because a half of 3 is 1.5. A half of this 3 is 1.5. And also a half of this is 1.5. So if you add 1.5 plus 1.5, you'll get 3. So this is the area supported by this beam. So the self weight of slab is equal to, you will take this length 3 times the thickness of slab is 150. So this is 150. Then you divide by 1,000, like that. Then times the unit weight of concrete, which is 24. So this one is equal to, so you have 3 times 0.15 times 24. So this is 10.8 kilonewton per meter. We also have the finishes. So finishes is equal to, we have 0.8 kilonewton per meter square, 0.8 kilonewton per meter square times 3 times 3. So this one will be 0.8 times 3. So this is 2.4 kilonewton per meter. Then the dead load, which is GK, will be the sum of these two. So this is 13.2 kilonewton per meter. So this is the GK. And then we'll proceed to QK, which is the imposed load. So this one is equal to, you'll take this 3 times 3 here. So this one is equal to 9 kilonewton per meter. And now this is the QK. So if I can rub here, if I can rub this plan, so we'll say that the ultimate load, the ultimate limit state load is equal to 1.4 GK plus 1.6 QK. So this one is equal to 1.4 times GK, which is 13.2, plus 1.6 times QK, which is 9. So remember, the unit is in kilonewton per meter square. No, kilonewton per meter, like that. So let's carry out the operation. 1.4 times 13.2 plus 1.6 times 9. So this one is equal to 32.88 kilonewton per meter. So if I can draw the beam here with the ultimate load this is what I will have. So this is 32.88 kilonewton per meter, and the length is 6 meters. 6 meters. From this, you can now calculate the design moment and the design shear force. So design moment is equal to design moment using this beam. Design moment, which is M, is equal to WL square over 8, based on this type of simply supported beam. So M is equal to W is 32.88 times L, which is 6 square over 8. So this one is equal to 147.96 kilonewton meter. So you'll come here and say M is equal to 147.96 kilonewton meter. And then we'll now come again and calculate the shear force or reaction at A, which will be reaction at B, and this one is equal to design shear force, which is FV, which is given by this formula, WL over 2. So this one is equal to 32.88 times 6 over 2. So 32.88 times 6 over 2. So 98.64 kilonewton. Again, we'll come here and say FV is equal to 98.64 kilonewton, like that. After having done so, we'll now proceed to the initial selection. So initial section selection. So for initial section selection, so the plastic modulus must be greater than M over Py, which imply plastic modulus must be greater than M, which is 147.96 times 10 raised to power 6. So 10 raised to power 6, we are changing from kilonewton meter to Newton millimeter, and then divided by 275 times 10 raised to power 3, because we want our answer in centimeter cubic. So 10 millimeter is equal to 10 centimeter. What about if you cube? You will get 10 raised to power 3. 147.96 times 10 to power of 6 divided by 275 times 10 power of 3. So you get 538 centimeter cubic. So you take this value and go to the table to select a universal beam section in that table. So I will show you. So as you can see, this is our table, and we want to use the value you have calculated, and it is 538 centimeter cubic, and that is our plastic modulus. So we'll come here where the plastic modulus is. As you can see, just follow my cursor. So this is the plastic modulus. So we'll use the major axis, which is axis XX, and we'll pick a value that is higher than that. So we have a 538. So let's pick a value that is higher than that. So we have 540, 568. We have 568. We have 540, and so on. So we'll take 540. We'll go for 540 and pick all the what correspond to 540. So we'll begin by the section. So the section is 305 by 102 by 33 kilogram per meter. Yes, 33 per meter. And then we'll come and pick D, also B, small t, and the rest. So after doing so, we will now proceed with our calculation. So let me write it on the board. So from the table, you will say try 356 by 127 by 33 kilogram per meter, and then the plastic modulus, which is Sx, is equal to 540 centimeter cubic, which is higher than 328 centimeter cubic by 2. And then these are the properties. So these are the properties. So D is 348.5 millimeter, small t is 5.9 millimeter, capital T is 8.5 millimeter, root radius is 10.2 millimeter, D is 311.2 millimeter, B over capital T is 7.38, D over small t is 52.7, IXX is 8200 centimeter rest per 4, and then ZXX is 471 centimeter cubic. So let's now classify the strength of this section. Allow me to clean here. So you have said that Sx given in the table is 540 centimeter cubic. So strength classification. So for strength classification, we always use capital T, which is equals to 8.5 millimeter. So this time round, I will not show you the table for this strength classification because you have seen it several times. So I will go straight to the classification. So T, which is 8.5, is less than 16 millimeter. Therefore, the strength is equal to 275 Newton per millimeter square. And this is the Py. We proceed to section classification. And before section classification, let's calculate this value. So this one is given by 275 over Py. So this one is equal to, which imply 275 over 275, which is equal to 1. We now proceed to section classification. So for section classification, again, I will not show you how to the table for this section classification. If you don't know the table to use, revisit my previous example and you will see the table for strength classification and section classification. Or also, you can revisit my introduction to steel design to BS 5950. You will see this table, these two tables. For strength classification, the parameters that is given for strength classification, and also the parameters that is given in section classification, like the plastic, the compact, and the semi-compact. So let's now classify the section of this steel. So we will begin by the flange. So for the flange, we will use B over T. B over T, which is equal to 7.38. And this one, it is less from the table, it is less 9E, whereby this one, it will be 7.38 less 9 times 1. It will remain 9 because 9 times 1 is 9. You will say therefore, flange is class 1 plastic. Visit my introduction to steel design to BS 110. You will see these two tables for strength classification and for section classification. And then we proceed to the web. So for web, we always use this ratio D over T. So D over T from the table is 52.7. From the table of universal beams. Again, from the section table, from the section classification table, 52.7 is less than 80 E. Therefore, 52.7 is less than 80 times 1. If you multiply 80 times 1, it will remain 80. Therefore, also class 1 plastic. Like that. After doing so, you will say that the section which is 356, this is the depth, by 127 by 33 kilogram per meter is class 1 plastic. Is class 1 plastic. So we have now classified our section, which is 356 by 127 by 33 kilogram per meter, is class 1 plastic. We now proceed to shear strength. So shear strength. So if B over T, if B over T is less than 70 E, therefore shear buckling shear buckling will not be considered, will not be considered like that. So B over T is 52.7, which is less than 70 times 1. Therefore, shear buckling will not be considered. So we now proceed to the shear capacity. So shear capacity, before shear capacity, our FV must be less than shear capacity, and PV, which is the shear capacity, is equal to 0.6 PY times D times T. So this one is equal to 0.6 times PY, which is 275, times D is 348.5, times small t, which is 5.9, like that. Then times 10 to the power of -3, so that we can get our answer in kilonewton. So this one will be, you carry out the operation, 0.6 times 275 times 34, 348.5 times 5.9 times 10 raised to power -3. So this is 339. This is 339 kilonewton. As you can see, the design shear force, which is FV, is less than PV, which is 339 kilonewton. Therefore, okay. Remember, our design shear force is 98.64. So this is 98.64. So let me write it here so that you can see it clearly. 98.64 is less than PV, which is 339 kilonewton. Therefore, okay, like that. So after having done so, we will now proceed and check whether it is a high shear load or a low shear load. So check if it is a high shear load. or low shear load. We know that for a low shear load, FV is less than 0.6 PV, and for a high shear load, 0.6 PV is less than FV and is less than PV. So this is for a low shear load, and this is a high shear load, like that. So 0.6 PV, because this is the most important parameter to check if it is a low shear load or a high, we'll first calculate 0.6 PV. So this one is equal to 0.6 PV, which is 339. So this one is equal to 0.6 times 339. So this is 203.4. 203.4. 203.4. So let's now do the comparison. As you can see, FV is less than 0.6 PV, which is a low shear load. So you will say FV, which is 98.64, is less than 0.6 PV, which is 203.4. Therefore, a low shear load, like that. After checking if it is a high shear load or a low shear load, we now proceed to the moment capacity. Moment capacity. So moment capacity. So for moment capacity, when dealing with a low shear load, it's given by this formula. Moment capacity is given by Py as X, whereby this is the strength of the steel, which is 275, and this is the plastic modulus from the table, which is 540. So this one is equal to Py is 275 times plastic modulus, which is 540, then times 10 raised to power 3. Change this one, centimeter cubic, to millimeter cubic. So you will cube the 10. It will give you 10 raised to power 3. Because our answer will be in Newton millimeter, so you will divide by 10 to power of 6 to change it from Newton millimeter to kilonewton meter. So this one is equal to 275 times 540 times 10 to power of 3 divided by 10 power of 6. So this is 148.5. 148. 0.5 kilonewton meter, 148.5 kilonewton meter. So we now proceed to check if this value is within the parameters given or not. So for moment capacity for a low shear load, it should be in the range. So this one is given by this formula P, Y, S, X. So it should be less or equal to 1.2 P, Y, Z, X, X. So it should be less or equal to this value, or will be the value that will be obtained by this formula. So 148.5 must be less or equal to 1.2 times Py, which is 275, times Zxx is here 471. Then we will multiply this by 10 to power of 3. Change this centimeter cubic to millimeter cubic. Then multiply by 10 to power of -6, or you can divide by 10 to power of -6. So it's the same thing. So now by dividing or multiplying by 10 to power of -6, it means you want your answer to be in kilonewton meter. So this one is equal to 148.5. Let's see if it is less this value. So 1.2 times 275 times 471 times 10 to power of 3 times 10 to power of -6. So this one is 155.43. Therefore, okay. So come here and write moment capacity is equal to 148.5 kilonewton meter. So we proceed to moment due to on weight of the beam. So moment due to on weight of the beam. Remember, our section is or was, let me check it for you, 356. So our section is 356 by 127 by 33 kilogram per meter. So this is the depth of the section, and this is the width, and this is the mass of the selected universal beam steel. So we want to use this mass to obtain moment due to on weight of the beam. So we want to convert this mass, which is 33 kilogram per meter, to Newton per meter, then to kilonewton per meter. So we know that the gravitational acceleration is 9.81. So you take 33 times 9.81. By doing so, our answer is in Newton meter. So you will multiply by 10 to power of -3. Then our answer will be in kilonewton meter. So this one is equal to we have 33 times 9.81 times 10 to power of negative 3. So this is 0.32. 0.32 kilonewton per meter. Remember, this is unfactored load. So unfactored load. And it is the GK because it is the it is the self weight of the beam. So let's now get the factored load. So the factored load is equal to 1.4 times 0.32, which is equal to 0.32 times 1.4. So this is 0.448. 0.448 kilonewton per meter. So if this is our beam spanning at 6 meters, then this will be 0.448 kilonewton per meter. So M due to on weight is equal to WL square over 8. So this one is equal to 0.448 times 6 square over 8. So the answer will be 0.448 times 6 square over 8. So the answer is 2.0. The answer is 2.016 kilonewton meter, like that. Now we proceed to the applied moment. Applied is equal to moment, which is 147.96 plus this one, which is 2.016. So the whole of this is in kilonewton meter. So let's see, plus 147.96. So this is 149.98 kilonewton meter. It means the applied moment, is greater than moment capacity X. Therefore, section not okay, like that. So you will conclude by saying try another section. So you will go back again to the table and choose another section with a higher plastic value, higher plastic modulus, which is XX than 540 centimeter cubic. I think I show you how to do this. If you find this section is failing, or if the section has failed, so what you do, you'll go back to the table and try another section with a higher plastic modulus value, which is SX. than 540 centimeter cubic. Again, you will again obtain the properties and redesign again up to this point. So you'll check if the applied moment will be less than moment capacity. So if the applied moment will be less than the moment capacity, the section will be okay. But if the applied moment will again be greater than the moment capacity, then it means again the beam will also fail. So you go again and try another section until it passes these parameters. So I won't go back to the table again. I leave it that for you. I want just to continue with the question. So a point to note, if you are doing an exam, because you are working with time, because time is a key factor that determines whether you'll pass your exam or not. So if you find this section fails at this point, do not go back to the universal beam table and try another section, because it will waste much of your time. You will be doing the correct thing, but it will take much of your time. So continue with the question, but write a statement here, like I have done here. Try another section with a higher value, with a higher plastic modulus value as x than 540 centimeter cubic. So the examiner will know, you know how to design, you know how to follow the procedure of this design, and he will give you all your marks. But if you are practicing, you are now a structural engineer, and maybe you find this section is not okay. So what you do, you will go back to the table. I've shown you how to do this. I think it is in example 2. In example 2. So you will go back to the table and try another section using different values. For example, using different section values than this one. Again, after doing so, you will just follow the steps. You will check for strength classification, then section classification, then you will come to the shear strength up to this point. And if it passes the parameters, then you continue with your designing. But for our case here, I'm not going back to the table. You can do it as your assignment. So after this, we now proceed to deflection. I want now proceed to deflection. So deflection. So we have the permissible deflection. So permissible deflection is equal to span over 360. Remember, this beam is carrying this beam is supporting a floor which has finishes. So the span will be, the permissible span will be, the permissible deflection will be span over 360. So this one is equal to, span is 6 meters. So you'll change it to a millimeter. over 360. So this one is equal to 16.67 millimeter. After that, we'll come to induced deflection. So induced deflection. So induced deflection is given by 5WL raised to power 4 over 384 EI. So we said that E is the Young's modulus of elasticity, and for steel is always equal to 205. So E for steel is always equal to 205 kilonewton per millimeter square. Always remember this. You may not be given in your exam. It is something that it should be on your fingertips. So 205 kilonewton per millimeter square. So this one is equal to 5 times W. W is, our W here is 9, is the imposed load. Again, remember, I said that when you are calculating for the induced deflection, you always use the imposed load. Only use the imposed load and forget about the dead load. So our imposed load was 9 times our length. Our length is 6 meters. So you convert 6 into millimeter. So it will be 6,000 raised to power 4 all over 384 times Young's modular. Young's modular is 205. 205 times I. So I is here 8200. 8200. 8200. So then times 8200 times 1000 times 1000 times 10 to power of 4. So this 10 to power of 4, we are changing this centimeter raised to power 4 to millimeter to power of 4. And this 1000, we are changing from this 9. So we have 9 kilonewton per meter. So we want to have kilonewton per millimeter. So you divide by 1000 like that. I hope you have understand. So this one is equal to this is 5 times 9 times 6,000 raised power of 4 divided by 384 times 205 times 8200 times 1000 times 10 to power of 4. So this is 9.0. So this is 9.0 millimeter. So you will say that 9.0 millimeter, which is the induced deflection, is less than 16.67, which is the permissible deflection. Therefore, okay, in deflection like that. We now proceed to web buckling. We now proceed to web buckling. Now let's proceed to web buckling. Web buckling. So this is web buckling. So for web buckling, we know that PW is given by this formula. P, this is the buckling resistance, is given by this formula B1 plus N1 times T times PC, whereby B1 is equal to the bearing length, which is 75 millimeter. N1 is equal to D over 2, which is equal to 348.5 over 2 is equal to 348.5 divided by 2. So this is 174.25. 174.25 millimeter, and the T is equal to 5.9 millimeter. So PC is obtained in table given in BS10, obtained in table given in BS 5950 not 8110, 5950. And for you to enter into this table, you will need this slenderness ratio, which is equal to 2.5 D over T. So this one is equal to 2.5 times D over T. D over T is here, 52.7. 52.7. So this one is equal to 2.5 times 52.7. So this is 131.75. So let's say 132. This is 132. And then we will also need the value of strength of the steel, which is 275 Newton per millimeter square. So this, the slenderness ratio, and this will enable you to enter into a table given in BS 8110, and I will show you. So this is the table. As you can see, just see where my cursor is. So this is the slenderness ratio, and this is the strength of the steel. Ours is 275. Just see where my cursor is. So we have calculated our slenderness ratio to be 132. So we will come here where the slenderness ratio is 132. So there is no a slenderness ratio here which has 132, which is 132. So we will interpolate. So we will go for 30, a value which is slightly lower than 132, which is 130, and we will pick the value for 275, so which is 95. and we will come for 135 and pick 89. So let me write it on the board. So we have 130, which is equal to 95, and then we have our value here 132 x, and then we have a 135, which is equal to 89. After doing so, we will interpolate. So we will get the difference between these two. So this is 2, and the difference between this and this, so this is 5, and the difference between this and this, so this is 6, and of course between this and this will assume to be x, like that. After doing so, we will do the comparison and get the value of x. So you'll take 5, compare it with 6, then is equal to 2 with x, which imply x is equal to, you will cross multiply. So 5 times 2, then you divide by 5. So this is 12 you divide by 2. 12 divided by 2 by 5, not 2. So this is 2.4. 2.4. Like that. So we will take 95 minus 2.4. 95 minus 2.4. So this is 92.6. 92. So our value here is 92.6. 92.6. Like that. So we have everything in our formula. We can now insert these values in our formula. So let's insert these values in our formula. So our formula is PW, which is the buckling web resistance, is equal to B1 plus N1 times T times PC. So we said B1 is the bearing, which is 75, plus N1. N1 we said is N1 is D over 2. So this is 348.5 over 2 times T, small t, which is 5.9, times PC, which is 92.6. Then, of course, you will multiply it by 10 to the power of 3 so that you can get your answer in kilonewton. So let's carry out the operation. So we have 75 plus 348.5 over 2 times 5.9 times 92.6 times 10 to the power of negative 3. So the answer is 136. So this one is equal to 136.18 kilonewton. Therefore, 98, so FV is less than PW, which is 98.64 is less than 136.18 kilonewton. Therefore, okay, and no stiffeners is needed. We proceed to what we call web bearing. So let's proceed now to web bearing. Web bearing. So the formula for web bearing, so web bearing resistance is given by this formula. So web bearing resistance is given by this formula, B1 plus N2 times T times PYW, whereby B1 is equal to the bearing length, which is 75 millimeter. N2 is given by this formula, 2.5 into bracket capital T plus small r. So which imply N2 is equal to 2.5. Capital T here is 8.5 plus the root radius. This is the root radius, 10.2. So this one is equal to 46.75 millimeter, like that. And the PYW is the strength of this steel, which is 275 Newton per millimeter square. So the web bearing resistance is given by B1 is 75 plus N2, 46.75, this one, times T, small t, which is 5.9, then times 275 times 10 raised power negative 3. This 10 raised power negative 3, it enables your answer to be in kilonewton. So this one is equal to 200.89 kilonewton. Then you'll say FV is less than P, is less than web bearing resistance. Therefore, okay in web bearing. And that marks the end of the question. We meet again in my next session, but a reminder, if you have not subscribed to the channel, subscribe and hit the notification bell so that you may be the first person to be notified. We meet again in my next session, and tomorrow I will start column design.